Tonight we're going to be very sporty. You have to only take one look at me to realise that I am not very sporty at all, but lots of people get very excited about competitive sport, and for very good reasons. And I have to say I am one of those people who, despite being completely unsporty, I look at these sporting endeavours on TV and think, wow, that's amazing. But my mission tonight really is to convince you of the fact that actually, as a species, we are truly pathetic. And anything you see in the Commonwealth Games or the Olympics is absolutely trivial in comparison to some of the amazing achievements of microbes. So we're going to talk a little bit about all the spectacular achievements that various microbial species make and how they might compare to human athletes in the modern day. And we're going to start in a time-honoured fashion, just like that most famous of competitive organisations, the Olympics, okay, with our trial of speed. So you might know that the original Olympics in ancient Greece started out as a speed race, as a running race. And I love this particular picture, which is obviously not the original Olympics. This is the 1896 Olympics, and this is the running race. And I particularly like the state-of-the-art sports clothing being worn by the athletes, and even more so, the state-of-the-art clothing being worn by the race officials here. I'm not sure that the bowler hat was strictly necessary, but clearly was. So speed is still a big thing in competitive sport, and we talk a lot about competitive speed running, particularly sprint running, and I'm sure everyone listening to this knows that the current 100-metre sprint champion is, of course, Usain Bolt, who runs the 100 metres in under 10 seconds, which it takes me more than 10 seconds to think about whether I want a cup of coffee. So that is deeply impressive, but is nowhere near as fast as some microbes when you can scale them up. So, and the triumphant, I guess, winners of the microbial race are the bacteria, and in particular, the flagellated bacteria. And those of you who might have listened to one of the earlier lectures in this series might remember that some bacteria, lots of bacteria actually, have these things called flagella, which are these long, stringy kind of appendages coming out of them. Lots and lots of bacteria have these, and these are a device that allow bacteria to swim. To swim in your bodies if they're an infectious bacteria, or to swim out in the environment if they are an environmental bacterium. And you may recall that the way the flagellum works is by spinning like a corkscrew and pushing the bacterium through the water. And as I said, lots of bacteria have these. This is a graphical image of E. coli, Escherichia coli. We'll come back to that one in a second. This rather beautiful movie is of Rhodobacter, and you can see Rhodobacter here swimming. You can see its flagella spinning away and driving it through this fluid. But what we fail to appreciate sometimes on this scale is that this is a microscopic scale. These bacteria are maybe 1 or 2 microns long, so 1 or 2 thousandths of a millimetre long, far below the resolution that we can see. So this is all microscope imaging. And at this resolution, lots of interesting things happen in terms of physics. And I'm going to ask straight away for a volunteer to come and assist me with this bit of physics, preferably someone in the front row. Would one of you mind volunteering? Just come up. Excellent, well done. Bravo. I think we should give him a round of applause straight away. Come and take centre stage. What's your name, brave volunteer? Oliver. Fantastic, Oliver. A hugely dangerous experiment is about to be undertaken. Hold on, you're going to need a spoon for starters. There we go, don't eat it. So at the microscopic scale, bacteria swim, for example, in water or in I don't know, urine if you're feeling particularly unpleasant. And we think of those fluids as being very, very free-flowing. But you might remember from your physics lessons and chemistry lessons that water actually sticks together quite well. You get this surface tension. Anyone remember that from school where you looked at a measuring cylinder and the water is not completely flat, it's kind of curved because it's sticking to each other. Or if you drop a droplet of water on the ground, it doesn't go, it forms a drop because it's sticky. For us, that makes no difference to the experience of water, but for a bacterium that is on the same kind of level of scale as that water, it means that water is not felt in the same way that we do. In fact, it's quite viscous, and it's approximately the same viscosity as treacle. I should point out, no branding here, other brands of treacle are available. So Oliver, what I'm going to get you to do, I'm afraid, is this is your bacteria, could you hold the spoon? This is your bacterial flagellum. A real scale flagellum would actually be longer than this room, which would be a bit of a challenge. So we've got this very small scale. So I'm going to get you to, hopefully without smearing this all over this beautiful listed building, hold your treacle, stick your spoon in, and start stirring. Come on, put your back into it, man. Marvellous. So it's only going to take about an hour, don't worry. So this live demonstration of a bacterial flagella rotating really very slowly is not going to push Oliver very far at all. And in fact, most bacteria spin their flagella at about 125 hertz, so about 125 cycles a second. So if you could match that, please, that would be very impressive. Okay, thank you very much. That was a very good demonstration. Bravo. So these bacteria are not just swimming in something that's very easy. They're swimming in thick treacle, essentially. They're spinning their flagella 125 times a second. For those of you who love motor vehicles, that's about 7,500 RPM. So they're going really, really fast. And they're doing it essentially without pause. As long as they have enough energy, they will keep going. And that means that if we were to scale up one of those bacteria, so this is a typical E. coli. This is E. coli actually 0157, which is one of the E. coli strains that causes food poisoning. You can see again these flagella, and the rate at which it spins its flagella move this E. coli at a speed that, if it was scaled up to be the size of Usain Bolt, would mean they'd do the 100 meters in under 2 seconds. Is by no means the fastest bacterium, though. There's a whole group of bacteria, the Vibrios, which include organisms like Vibrio cholera that causes, you've guessed it, cholera. These are even faster, about 2 to 3 times faster. So a Vibrio, like this one here, will complete the 100 meters at scale in less than 1 second. Or, if you want to really scale that up, because of course they're doing this the entire time, if you want to scale it up, that Vibrio would complete the London Marathon in just over 7 minutes, start to end, which I think is quite impressive, and I'm afraid far more deserving of those gold medals than anyone who's done this at the Commonwealth Games. In treacle, I would point out, in treacle. Okay, so speed is the first of my medals to be awarded tonight into the microbes. But it's by no means the only major achievement, of course, in terms of medal-winning activities. And so my next one that I want to turn to is this one. This is the one that actually makes, I can't watch weightlifting because it kind of makes me go, it's quite scary. This weightlifting, you might know, the current men's prize gold medal for weightlifting is to lift a dead weight of 267 kilos. Which is about 3 of me, actually. So that's quite a substantial amount of weight that someone human has lifted above their head. But once again, relative to microbes, this achievement in terms of weightlifting is actually fairly pathetic. So if you're lifting 267 kilos above your head, which it doesn't even bear thinking about, but if you were lifting that weight, the pressure on each of your feet is about 100 kilopascals, about half the pressure of an inflated car tyre. Okay, so if that kind of makes sense. So that's why, for example, if you might kick the tyres on your car, but you can't push your foot right through them because you can't exert that kind of pressure. So when you're carrying a weight like this, you've got about half a car tyre's pressure on your feet, or about 100 kilopascals. But to look in the microbial world, we can find examples which exceed this by many orders of magnitude. And this is the best example I can come across. This is a picture of rice, okay? Rice as in the rice you eat. It's a rice field, and those of you who are sharp-eyed will notice that the middle of this rice field is sort of yellow and brown. This rice field has a disease called rice blast. And rice blast is globally a major problem. It causes huge losses of rice yield right around the world. And it's caused by a fungus, Magnaportha oryzae. That fungus lands on the leaf of the rice and then penetrates into the leaf, moves its way through the plant, and then starts to produce spores, slowly killing the plant, but also spreading itself remarkably around the whole field in a very, very short period of time, actually. To do that, the fungus has to penetrate through the leaf and start growing inside it. And this rather lovely video you can see here, you can see that process happening. So you can see the fungus coming into a plant here at the top. And what you will see as it grows, every so often it hits a plant cell wall, it pauses, it builds up pressure, and then it pops through into the next one. And over a period of several hours, you will see that this living plant is slowly being invaded by this fungus. To do that, the fungus has to produce a very high pressure kind of point of penetration to get into the plant in the first place, something called an aprosorium. And this is what that process looks like when you are on a leaf surface. So this is the spore of that fungus landing on a leaf surface. and it's about to try and penetrate. And what you will see in this video is that it extends out a growing tip, and then it puts all of its effort into forming this blob up here, this aprosorium. And this you can think of a little bit like that kind of, that needle that you use when you're inflating your car tyre, that high pressure injection point. This is performing the same function for the fungus, but at a remarkable level. The pressure inside this point here is 8 megapascals, so 40 times more than the pressure on that person's foot when they're lifting those 267 kilos above their head. And in fact, if you were to scale this up, this fungus, as a weightlifter, would be lifting in the region of around 27 tons above their head, or the weight of a Chinook helicopter, which is, I think, far more impressive even than those kind of, scary dumbbells that people lift up above their heads on a regular basis at the Olympics. This turns out to be hugely interesting, of course, not just because tackling this plant invasion is the key to stopping this terrible disease decimating crops, but also because there's lots of interesting kind of chemistry and physics here about how does a tiny fungal spore generate such a massive pressure, how does it stick onto the leaf to get into there in the first place, and how does it recognize the right surface? It doesn't do this everywhere, fortunately, because of course if it did it everywhere, you might come out one morning and discover your car tyres are all flat because it's blown holes in all of them. But it doesn't do that. It only does this on its host plant. And so there's lots of interesting kind of molecular biology understanding how this process works. Okay, so we've covered speed and we've covered weightlifting. And that weightlifting model, we're talking about pressures, right? We're talking about lifting something above your head and exerting a huge pressure on your hands or on your feet. But there are different sorts of pressure. That's one kind of pressure, lifting something up. But as these rather excellent people noticed many years ago, there's lots of different ways of being under pressure. And lifting something above your head is one of them, but having an even pressure from the outside is another sort of pressure stress. And if anyone's been diving in the past, you will know about this feeling of pressure, because when you enter the water, obviously water is denser than air and you get a pressure around your body. And the deeper you go, the more that pressure applies. So, and roughly speaking, about every 10 meters that you go down, you get one more atmosphere of pressure. So the first 10 meters, your normal atmospheric pressure is doubled, and so on and so forth as you go deeper. And that means that for humans, which are kind of basically quite squishy organisms, there is a fundamental block on going very deep at all. And in fact, what you see here is this is someone who's doing free diving. And so free divers typically go down maybe 30 or 40 meters, but no deeper. And the current world record for free diving is actually an absolutely amazing 200 plus meters, 211 meters, I think, which is really, really deep. But exerts an enormous pressure, about 21 atmospheres of pressure on that free diver when they're that deep. So they can't stay down there very long at all. They go down, they come back up very fast, and they have to do it under massively trained conditions because the risk in doing that is absolutely huge. Humans are not good at dealing with external pressure at all. 200 meters of ocean depth feels like quite a lot of depth to me, particularly because I'm not a very good swimmer. But actually on the scale of the world's oceans, that's barely skimming the surface. Most oceans are far, far deeper than that. And some are really very deep indeed. And this is, of course, the deepest one in the world. This is the bottom of the Mariana Trench, the deepest part of the ocean. And it's over 10 kilometers from the sea's surface. Down to here, this is a photograph taken from the submersible that went to the bottom of the Mariana Trench. When you look at a picture like this, 10 kilometers down, you might think, and it would be very reasonable to suppose, that this is a completely lifeless environment. But that is not true. And in fact, samples recovered from the bottom of the Mariana Trench demonstrate just how well microbes can cope with these extreme conditions, because in one of the samples recovered from that trench fairly recently, we found this. So this scanning electron micrograph shows you little lumps here, which might look a bit unappealing, but these are in fact individual bacteria. This is a species called Colwellia marinae, which is a bit of a mouthful, recently identified living at the bottom of the Mariana Trench, under a pressure that is about 1,000 times more than atmospheric pressure. It's absolutely extraordinary. So this is many, many, many hundreds of times more than humans can cope with. It's more than most submarines can cope with. It's more than most human-built things can cope with in any condition. And yet this bacteria is apparently thriving, growing quite happily in that environment. We know very little about this bacterium, not least because it's quite hard to work with an organism that grows under 1,000 atmospheres of pressure, because as soon as you bring it back to normal room conditions, the thing explodes and you can't study it. So to study this organism, you need to recapitulate those unique conditions from the bottom of the Mariana Trench and try and grow it under massive pressure, and that is not something that most laboratories are able to do. But nonetheless, I think there are fantastic lessons to be learned from this organism and other organisms like it, because it is doing something that we don't understand how it's feasible. We don't understand how a biological, squishy entity like ourselves can live under the pressure of 1,000 atmospheres. And I think understanding how that process might happen is the key to understanding lots of interesting things. For example, how we might send probes to parts of the universe where we haven't been, where pressures are very different. How we might design new structures to withstand very high pressure or indeed very low pressure for human benefit. All of these questions potentially might be informed by studying organisms like Colwellia and other microbes living in these kind of extreme conditions. The interesting thing about thinking about this particular organism is if we scale it back up again, as we're doing for the whole of this evening's lecture, into human terms. So here we have an organism living 10 kilometres down at 1,000 atmospheres of pressure. And so the pressure on this bacterium is about the equivalent of one of us balancing not one African elephant, but 100 African elephants on the end of our nose. So if anyone fancies trying that later, feel free. But I think this perception of pressure is really beyond anything that we can kind of easily rationalize as humans. Okay, so we've talked a little bit about pressure on the outside, pressure on the inside, and I want to change now and think a little bit about time and about speed. And one of the things is not in the Olympics, obviously, but it's a record that we often talk about is around lifespan. I don't know if anyone else saw this last week, the world's oldest dog. I was very excited by that. 31-year-old dog in Spain or Portugal, I can't remember which. These kind of news stories crop up again and again in the news. World's oldest tree, world's oldest dog. I saw world's oldest pancake once. I'm not sure how you validate world's oldest pancake. But anyway, we're obsessed with things that live for a long time or things that live for a very short period of time. And of course, as humans, we're also quite obsessed about our own lifespan, extending it, preferably extending it well, so you live healthier as well as longer. And so there's a lot of interest in understanding how other organisms' lifespan is controlled. And within the microbes, you have both extremes, both kinds of medal, the fastest and the slowest. So if we think about the fastest, for example, the fastest that we know of are bacteria, and in particular, the same bacteria I mentioned at the beginning, E. coli, Escherichia coli. E. coli is, if you like, the kind of laboratory mouse of microbiologists. We have studied this bacteria for 100 years. We know all the genes in that bacteria. We know how it builds its cell wall, all sorts of interesting things about it. And we have a variety of lab strains that have been essentially optimized to grow as fast as they can. And the fastest of those will divide about every 17 minutes. Okay, so in the time I've been talking, we've already had more than one division of E. coli, and there'll be another one before I finish. You'll be disappointed to hear. They go incredibly fast, and that is because most bacteria, including E. coli, divide by this process of binary fission. So one cell elongates, divides, and forms two. And you can see that in this movie here. So you see a bacteria here elongating and dividing into two, elongating and dividing into two again. This process, when you look at it, it's actually quite beautiful, but also feels sort of very, I don't know, like a bit like a ballet, isn't it? It's very gentle. But the scale at which this can impact on the things we understand is quite remarkable. Dividing every 17 minutes doesn't sound too crazy, but actually has a really big impact. And let me demonstrate that by a bit of an analogy. I'm going to need some more volunteers for this, I'm afraid. And my very high-tech equipment here. I pre-counted this. So we're going to do a little bit of audience participation, but I've pre-counted where I'm going to go. And I was going to start, I have to remember, with this gentleman over here. Could you stand up, please? And you can wave at the camera now. Sorry, what was your name? John. John is our E. coli, and he gets the really exciting prize of a single grain of rice. There you go. Don't say you don't get anything when you come to a Gresham lecture. There we go. And that grain of rice demonstrates our 1 E. coli. Now, every 17 minutes, that grain of rice is going to double, okay, to another one, because it's growing optimally, okay? So we're going to go now about 3 and a bit hours over, so that's about 10 people. I'm going to go over to this gentleman over here. Can you stand up? What was your name?
Alex.
Alex, brilliant, Alex. So now you are going to get the big prize, okay? You're going to get some of these. There we are, for your own rice. So we're into, sorry, just scattered rice all over you here, there we go. We're in now 10 generations on, okay? And actually, by the time we get there, that 1 grain of rice, you get a really big prize, Alex, to take home with you, is a whole kilo of rice, okay? So that doesn't feel that much. 10 generations, okay? We've gone from 1 grain of rice to a kilo of rice. But, and that's in about 3.5 hours, something like that. We roll the clock on now, and imagine this is an infection, right, in your bloodstream, for example. A kilo of bacteria would be pretty scary, actually, but nonetheless, it's not a huge difference. But if it keeps going unchecked, by the time we hit to 12 hours, which was over here somewhere with this lady, I think, can you stand up? What was your name? Samantha, fantastic. Samantha, you get the really big bonus prize, which you'll be pleased that I have not brought. So at 12 hours in, okay, which is you, that single grain of rice is now about 10 tons of rice, which would easily fill this room, in fact, and feed about 10 million people a decent rice to go with their curry tonight. So in the period of 12 hours, we've gone from something that's almost invisible to something that would fill this entire room. Thank you, volunteers. You can sit down and take your 1 grain of rice or kilo round. We have got, so this power of exponential growth has taken a single bacterium that you can't see to filling an entire room. And in fact, you can scale that out. And if you think about that in the context of something like sepsis, this is why sepsis in a patient is so incredibly dangerous. Because if you miss it for a few hours, what is an initial few bacteria becomes an overwhelming infection. And it's the same reason why something like that rice blast infection in a field, you have to catch very early. Because if you miss it and it's doubling every couple of hours, it's far too late to intervene when it's progressed and established. So that pace of growth is truly astronomical. And of course, far faster than any other organisms we know about. The only exception, I think, in the microbial world is that, of course, these bacteria are the fastest growing free-living cells. But all organisms have parasitic viruses that live within them, and bacteria are no exception. There are lots of viruses that live in bacteria, and those viruses, when they're in their host, can be replicating much, much faster. And many of us in this room will have experienced that in the last few years when you've had your own virus and realized just how fast these things replicate. So although an E. coli might replicate every 17 minutes, inside an infected E. coli, you might have a single virus turning into 100 or even 1,000 virus particles in the same period of time. So actually, the real fastest growers in the universe that we know of are those viruses. But they, of course, cannot replicate without a host. So their speed is still determined by something else. So I still think if I was going to award the gold medal for speed of replication, it would go to E. coli for its 17 minutes. So that's a prize for speed, for going really, really fast. But what about the alternative? What about going really, really slowly? You might anticipate that in the microbial world, slow is bad, and often that is true. Certainly, if you were going to be a pathogen spreading on a field of crops, being a slow grower is a very bad idea. If you want to cause an infection, a urinary tract infection, and you take 6 weeks to do it, you're never going to be a very successful pathogen. But there are environments where being a slow grower can be kind of beneficial. And in particular, those are the environments where life is really tough. In fact, where you might imagine that life is impossible. But if by growing very, very slowly, you can contend with those challenges that the environment throws at you, you can deal with a lot of the problems that other organisms might not be able to tackle, and you can survive and you can grow, albeit very slowly. And so it's in those extreme environments that we find some of the slowest growing microbes that we know of. And actually, I think personally, those extreme environments are one of the places where we need to do a lot more hunting because there's a lot of really interesting biology there that we still know very little about. And here, just to demonstrate that, is an example of one of those microbes that is truly, truly slow. In fact, it's kind of ironic that it's so slow it hasn't actually got a name yet. So this slightly blurry image you see in front of you shows you, and you're going to have to believe me here, some bacteria. These little blobs, these are round blobs, they look totally bland, right? I'm not sure that anyone would be convinced by this. If I said this is definitely a bacteria, you'd probably think, really? That looks like I don't know, someone sneezed on the camera. But it is. And we know that because in these slices, we can provide, for example, chemicals that the bacteria need to grow. And we can look to see if those chemicals become incorporated into cells. And if they do, then you know that this apparently bland blob is indeed alive, a bacteria. So this sample here with these bacteria in is one of the oldest, slowest types of bacteria we know of, because this sample came from here. This is Beacon Valley in Antarctica. And as you can see, it's a pretty desolate place with a long-standing glacier here, from within which an ice core was taken. And in that ice core, this so far unnamed bacteria was found. We can do isotopic analysis of that glacier, essentially looking at the water that composes it, and because the ratio of different isotopes in the atmosphere has changed over time in a way we know, you can date essentially the ice. You can say, when did this ice form? And it hasn't melted since. And when we do that for Beacon Valley, the age you get is about 8 million years. So this bacteria and its friends have certainly been isolated from the rest of the world for the last 8 million years, living inside this ice tomb, if you like. We don't know how fast it's been growing in that period of time. We know it's astronomically slow. We don't know how fast. But by a little bit of kind of jiggery pokery and looking at the same incorporation of isotopes into those cells, you can get a rough estimate. And the rough estimate is that this bacteria divides about once every 10,000 years. Which means that the ones that you see here in this picture were born, if you like, at a time when saber-toothed cats were roaming the world, where woolly mammoths were, where we are now, at a time when civilization as we know it did not exist. And in fact, if you roll the clock back a few more generations, those generations we just saw in a 12-hour period for E. coli, if you do the same experiment for this bacteria, it would take about 500,000 years to go back the same distance. So you have two bacteria, two microbes that look rather similar, this nameless one, an E. coli, whose difference in speed, one dividing every 17 minutes, one every 10,000 years. I think that's quite impressive. Even more impressive is very recent data suggesting that this is not even the oldest, the slowest. An even more exciting core, and this is perhaps slightly easier to see bacteria here in these images. This is a slice, not of ice, but of rock. And this slice of rock is taken from about 60 meters under the seabed, at a point in the sea in the Pacific Ocean where there's already about 2 miles of sea above you. So this is a very deep section under a huge amount of pressure. And it's actual rock, so this is not sort of loose sediments where you can find mud. This is a solid piece of rock that has been sliced, and inside that rock we can find bacteria. Again, no name as yet. In fact, maybe we should have had a competition to suggest names for this new species. But this species, and you can do some very nice chemistry here also and demonstrate that these are alive, and they are living inside this high-pressure rock environment. And by the same process of isotopic analysis, you can work out that that rock has not seen daylight, or has not been open, for about 101 million years. We have no idea still how fast this reproduces. We know it's very slow. Maybe it's 10,000 years like the other one. But certainly this population of bacteria has been in that rock since well back into the time of the dinosaurs and before. And possibly only dividing maybe every 100,000 years, perhaps every million years, incredibly slowly. This, aside from being an interesting piece of trivia to share with you on an evening like this, I think is a really key and important piece of biology, because although growing really, really slowly is a way to deal with these extreme environments, you still have to deal with the challenges that we all have to deal with. For example, the chemistry challenges. Over these enormous periods of time, a lot of molecules degrade spontaneously. A lot of things that are harmless on a day-to-day basis, like sunshine, for example, are not harmless over millions of years. You get huge amounts of UV damage. Things like cosmic rays, which occasionally shoot through the Earth, but very, very infrequently. But if you're going to be around for a million years, very, very infrequently still starts to be a bit of a problem. And so, in a way that we don't understand, these organisms must have an ability to deal with this kind of damage and repair it on a very, very slow timescale. And learning how they do that could, I think, be very, very useful for us, actually in very, very applied situations. For example, in cancer therapy. So when you do cancer, a lot of cancer therapies essentially rely on creating DNA damage to try and destroy your tumor, but you don't want to create DNA damage in your other cells. And so understanding about how these organisms repair that kind of DNA damage might help us learn some tricks for that very applied branch of medicine. Okay, so that's very fast and very slow. Let's go back for a moment to our sports, and let's think about some other sports for which people get lots of medals. And this is one that I was so bad at. I remember at school, this is the shot put. I was so bad at, I had one go, and my PE teacher, I remember saying, "Robin, I think it's probably time you tried a different sport." I think he was worried for himself as well as for me. So shot put is obviously where you take essentially a mini cannonball and you throw it a very long way. It's one of the interesting sports which over the last 100 years has been consistently and fairly linearly getting further and further and further. But still, we're looking today at records in the region of sort of 20 to 30 meters max for throwing this projectile out. Still very impressive, but nowhere near as good as Microbes. And this is my front runner for the gold medal in the shot put for Microbes. And this is the rather beautifully named artillery fungus. I love that name, Spherobolus. And it looks fairly innocuous. You can see here growing on a piece of rotting wood. This is quite zoomed in. This is actually a very small fungus. If you walked past it in the woods, I don't think you'd notice it. It's one of those many, many fungi that decompose dead and decaying wood in forests. It's tiny, but like all fungi, it needs to spread, and it's tricky, it can't run around. It needs to get its spores out into the environment to spread around, and it does that, as the name might suggest, by shooting them, okay? And it shoots them really in a most amazing way. So each of these, if you zoom in, forms this tiny kind of star-like or egg cup-like structure with a ball in the middle. This is your shot for your shot put, inside of which are lots and lots of fungal spores. And what the fungus wants to do is to get this as far away from all its competitor fungi as it possibly can. And it does that by shooting it. And you can see that here. Sadly, there's no sound on this video, because you can also hear it even. You can hear it going, but you have to imagine the because there's no sound. Here we have our fungus growing in its media, and what you'll see here is one of them shooting its little spore at a truly amazing distance. In fact, this is without scaling, right? In real life, these tiny, tiny spores leave at about 20 miles per hour and go about 6 meters. So this is for a fungus that you can barely see on the ground, crossing almost the width of this hall with its spore. And if we were to scale that to our human shot putter, as we've been doing all evening, then for those of you who are here joining me in the hall, the current world record for shot put for a human would get your shot from here to about the street you came in off, okay? Which is not, for those of you joining online, that's not a very long walk. It's about 25 meters. This fungus, if it was here in the hall doing the same thing, would throw that shot just over 1 kilometre and would be breaking windows in the British Museum over on Holborn. It's a really, really impressive feat. And once again, I would remind you that at this scale, it is doing this not through the kind of normal environment that we experience. It too is experiencing this very gloopy kind of media that's a bit more like treacle than it is like water, and yet still hurling its spores these astronomical distances. So gold medal for me goes to the artillery fungus for the shot put. So for the last 5 or 10 minutes or so, I'm going to turn my attention away from some of these kind of more classical sports and achievements we do to areas where, fortunately, perhaps, we do not have human records to beat, but to try and demonstrate to you that microbes have some other really amazing talents that we should be thinking about. And in particular, these talents, if you like, have had a major impact on human civilization. And I've classified them into two areas, triumph and disaster. The triumph is the ability of microbes to endure conditions that, for most humans, are far beyond anything we can possibly experience. And my winner of the medal there is this little chap here. This is Deinococcus radiodurans. I love that name. It's another bacterium, and excuse me, which grows actually typically as a pair. So these are two cells stuck together. They usually grow like this. And there's a rather beautiful story about this because this bacteria was discovered by chance, but as a product, if you like, of human innovation. For those of you who've listened to one of the previous lectures in this series, you might recall that we talked a little bit about food poisoning, and we talked about canning and bottling and a way to preserve foods. And we met this rather nice lady here back in the 1920s who is demonstrating just how excited we can get about bottling things as humans. And for those of you who weren't there, let me just recap. The point about food, obviously, is it spoils most foods. If you harvest, I don't know, beetroot and you leave it on the side, it will rot and it will go horrible. If, however, you can keep it in an environment away from air, you will dramatically slow its rotting because most microbes need air, and so if you can keep it away from air, it won't rot as fast. And that, in essence, is how humans invented things like bottling and canning to keep air away. And we talked in the previous lecture about the fact that that works pretty well for most things, but there are some microbes, in particular, some of the most toxigenic ones that create toxins, that actually quite like being away from air, and so you can get these really unpleasant toxin-based illnesses from canned food. Now, in the context of that, so back in the sort of 1930s and 40s, when canning and bottling was really taking off, there were serious issues with people getting quite sick from those foods, because you might recall that we talked in one of the previous lectures about botulinum toxin, this incredibly dangerous bacterial toxin that is associated with canned food. So lots of people were aiming to try and find out what is causing this toxin and how can we prevent it getting into our cans. Now, back in the kind of 40s and 50s, the other big thing that was happening, of course, was the discovery of nuclear energy. Okay, we'd had the nuclear program in the United States during the Second World War, and there was the start of, I guess, what was the nuclear revolution. So people were starting to think about nuclear power as a source of electricity. And there's, I don't know if you go back to the 1950s, there were some fantastic ideas there. I saw nuclear-powered backpacks for people so you could kind of carry your office around with you. And my favourite one, which is true, I discovered recently, that apparently in the 60s you could buy nuclear peanuts, which were peanuts that had been deliberately irradiated. And they were kind of really cool and swanky and exciting thing to serve at your cocktail party, was a nuclear peanut. I'm not sure it would catch on today, but anyway. This is a period of time when people were really excited about radiation and the potentials. They hadn't really appreciated the dangers at that stage. So one wise group decided, radiation penetrates things. That's the whole point, right? You're not safe just stood behind something thin because radiation goes through. Why don't we use radiation to sterilize our tins? So we'll bottle our food and then we'll pass it across a radiation source and we'll irradiate it and it will be sterilized and everything will be fine. So they tested that. And were very shocked to discover that still they got cans that would go off and would rot. And the reason for that was because those cans had this guy, radiodurans, living inside them. And it turns out that this organism is capable of withstanding unbelievable levels of radiation. In fact, it will withstand so much radiation that it will withstand about 1,000 times the lethal dose of a human. Okay, about 5,000 Gray, measuring Grays. So about 3 to 4 Grays of radiation is enough to kill a person within a few minutes. Radiodurans will happily take 1,000 times that dose, which is the equivalent, actually, of it essentially surviving unharmed ground zero underneath the Hiroshima atomic bomb and just carrying on as if nothing particularly happened. It is amazingly good at withstanding these intense radiation sources. That on its own right is very interesting, but it's also extremely important because, as you will be aware, radiation is essentially one of the major limitations for space exploration. At present, we can't think of a way to get people to Mars safely because there is too much radiation dose that those people would experience, those astronauts would experience, on the way to Mars. We need to find a way to either shield them from it or to make that damage less dramatic. This bacterium has found a way to repair and to protect itself from radiation damage on a scale far beyond anything that's out there in space. And so maybe by learning more about that, we will have a clue as to how we might be able to better improve our own tolerance of radiation, for example, for spaceflight, or indeed, much more prosaically, in things like X-rays or CT scans. So let me finish with possibly the most grim, but also from my perspective as an infectious disease person, the most interesting kind of medal-winning part of microbiology, which is those microbes that have won the kind of infamous medals for being the most destructive in the history of humanity. There is no one in the world today, I suspect, who hasn't witnessed firsthand the destructive power of microbial pandemics over the last few years. And I think it's sometimes very salutary to learn that the appalling burden of COVID-19 is still nothing as compared to some of the pandemics that have happened in the past. And so it's very hard to work out just how dramatic many of those historic pandemics have been. But here, for what it's worth, are my kind of top three in reverse order. So our bronze medal here goes, I actually thought when I was doing my homework for this, I thought this would win, but I was wrong. So this is the influenza virus. And I suspect many of you, like me, will have been reading recently comparisons between coronavirus and influenza, and in particular the 1918 pandemic flu, sometimes called the Spanish flu. So in 1918-1919, a new strain of influenza arose, spread very rapidly around the world, particularly on the back of all the human movements that were happening at the end of the First World War, people returning to their countries from all over the world, spreading with them this new pandemic flu variant. This was an extremely violent, virulent form of flu that had a very high mortality rate. People argue, so the flu itself was very virulent, undoubtedly, but also, of course, the population was vulnerable. We'd had this terrible war for 4 years, and people were malnourished, often living in difficult conditions. So there was a double vulnerability there. And in that about 18 months that pandemic raged, we estimate that about 40 million people died. And at the time, in 1918, that's about 2% of the human population. So that's a really big number globally. But still not. That's only enough to get you into the bronze medal position in this rather grim final slide here. This silver prize winner is another virus, though. This one is one that hopefully most of us in this room have never encountered. This is smallpox. Okay? Smallpox is a viral infection of humans that has been with us for probably most of our modern history. So there's very good evidence of smallpox, for example, in ancient Egypt. So it's certainly been around humans for a long time. But it comes in waves. There's been particular waves. And the big wave that is particularly dramatic is the one that occurred after Europeans discovered, and I use the word advisedly, the New World, the Americas. So you might be familiar with this story that, of course, ships from Europe discovered America. People started to move from Europe to America. Unfortunately for them, there were already people living in America. Unfortunately for the people who were living in America, this did not end well, primarily because smallpox was a virus that had evolved in Europe and Asia for many hundreds of years, thousands of years probably, prior to the discovery of the New World. Human populations in the New World had not previously experienced this virus. As far as we can tell, the virus was not present there, and so they were completely vulnerable to smallpox. Smallpox swept through those native populations, and in some cases, particularly egregious cases, was deliberately promoted by invading colonists as a means of clearing the land. So they would, for example, give Native Americans blankets that had been slept in by smallpox patients in order to try and eradicate the people from the land they wanted. And that pandemic that arose from that colonialization of the New World in particular is estimated to have killed about 50 million people. That's more than influenza, but most strikingly, I think, we estimate at the time that the entire native population of the Americas was not much more than that, actually. So this is about 90% is the estimate. 90% of indigenous peoples in the Americas were killed by smallpox. It caused an extinction level event of that whole branch of humanity as a result of a pandemic. But even that very grim lesson is not as bad as my final gold medal winning one, which is not a virus. This is bacterium. This is Yersinia pestis, the cause of the bubonic plague. Once again, an organism that has been with us over most of human history. We have known multiple waves of plague, but the one, of course, that is ingrained in all our consciousness is the Black Death in the Middle Ages. This particularly virulent form of plague came out of Asia along trading routes, along the Silk Route in particular, into Europe. And because this was a time of great movement, but also of great urbanization of Europe, lots of people moving to cities, for example, like London, like the one we're in now, and therefore it gave the opportunity for the Black Death to spread very, very swiftly, which it did with quite startling efficiency. And in fact, during the 7 years of which the Black Death was most rampant, this is estimated to have killed about 200 million people. At the time, this is 50% of the entire world's population within a 7-year period. Okay, and so it's for that reason that even today you can visit medieval churches and you can see these, rather beautiful scrolls asking for, divine intervention because the end of the world is here. And it's quite reasonable, I think, to assume if you were in a village where half the village had died in the last 7 years, you might think that there was no way out of this except by divine intervention. And this is still, as far as we know, the most deadly pandemic in the history of humanity. That's a really gloomy note to end on. So let me finish with one last slide, which is a little bit more upbeat about our record breakers, which is thinking forwards. This is a kind of selection of random record breakers tonight, but there are so many more records out there because we have no idea, actually, how many bacterial species exist. But we estimate there might be as many as 1 billion different bacterial species on the planet. That's a big number. Pales into insignificance when you consider the number of individual cells, individual bacterial cells, which is very, very loosely estimated at 1 million trillion, or one with 30 zeros at the end of it, types of cell. Each one of those cells, of course, is slightly unique. There are mutations, there are changes, and so there are 1 million trillion opportunities for differences, for startling new biology, for remarkable physiology. And so I think when we start digging further and further, as we start to do now, particularly with the advent of really high-scale genetics to go and look in places we haven't previously looked for these organisms, we'll find lots of opportunities, lots of really exciting new biology, and hopefully in a few years from now, someone else will stand here and tell you a whole bunch of new records that have been broken by lots of new bacteria that we don't know exist. And let me finish there. Thank you very much for listening.
Thank you very much. Thank you, Professor May, for this very interesting lecture. We have now time to take a few questions, so we'll start with our online audience and then we'll open up the floor for questions. So first a question more on the archaeobiology term and perhaps global warming. So will melting permafrost release ancient viruses and microbes, and what could be the consequences of this?
That's another doom-monger question to start off with. So the short answer is quite possibly, I think. So what do we know? We know that there are large areas of permafrost obviously all around the world. We know that many of those areas have not melted for millions of years, like the example I gave in the lecture. We know that lots of microbes can survive perfectly happily in those conditions. So all of those things would lead me to believe that melting permafrost will release organisms that are kind of new to science in the sense we haven't seen them. Why am I not kind of running from my bunker? I guess the saving grace there is that for those to be the next pandemic, they would have to be pathogens of humans. And I can't think of a reason why a bacteria 8 million years ago would be optimized to live on a human, which didn't even exist at the time. So I think for most organisms coming from permafrost, the chance of it being a major human pathogen is very, very slender. What might be much more serious, though, is the chance of it being, for example, agriculturally relevant pathogen. So you could imagine something that lived quite happily on ancient kind of ancestors of cattle that's tucked away in permafrost somewhere and kind of comes out and it is optimized for living on cows today. So I think it doesn't keep me awake at night, but I would say it's a non-zero risk, definitely.
And perhaps could those, because of these extreme circumstances, could they be perhaps a learning point from, extraterrestrial life or microbes or this sort of environment?
Yeah, absolutely. So astrobiology. So there's a lot, I think there's a lot of interesting things, particularly those extreme environments. So the organisms that live in very low temperatures, the ones that live in extreme radiation areas, the ones that live under massive pressures. Those conditions exist, we know, on lots of other planets. And people might be familiar with a lot of interest in Europa, for example, as one non-Earth type area where there might be life. Looking at exoplanets, we now know the existence of several hundred planets that are orbiting other stars, some of which are in what's called a habitable zone, so they're in a temperature area where you could have life. So looking in those places, you might well want to look for the kind of microbes we're talking about in terms of extreme microbes, rather than your kind of run-of-the-mill microbes that you find in ambient conditions, because it's the extreme environments where you might be more likely to find those, life on other planets. So, yeah, it'd be very exciting, wouldn't it? I'd be very excited to find life on other planets. We'll see.
Another question, this time perhaps more in the medical term. In terms of cell biology and biochemistry, what makes fungal infections so difficult to treat?
Right. What makes fungi? So why are fungi hard? I guess the question is, why are fungi harder to treat than bacteria or viruses generally? And the simplest answer to that is because they're much closer to us. So in terms of evolution, bacteria are, it's been a very, very long time since we've shared any ancestry with bacteria. Fungi are eukaryotes, so they're like us. They have a nucleus in their cell, for example. Their biology is much more similar to humans than bacteria is, which means if you're trying to design a drug that kills it, it's much harder to come up with a drug that kills a fungus specifically and doesn't hurt humans than one that kills bacteria. And that's one of the reasons, if anyone's unfortunate enough to have had a systemic fungal infection, that often the drugs have quite nasty side effects because they're not perfect. So that's one reason. The other reason is the fungi are very good at many fungi go to growing in places which are really difficult to treat. I'm sure lots of people in the audience have had the delight of, for example, a toenail fungal infection. They penetrate into this toenail. Toenail is quite hard to get drugs into. Fungus doesn't mind, but it's quite hard for us to treat. So there's this combination of where they're growing and the fact that they are much more similar to us makes them very, very tricky.
All right. Well, thank you. Any questions from the audience? I'm just going to wait for my colleague to pass the microphone. Thank you.
You talked about a microbe, bacteria, and also viruses. Is bacteria and viruses both microbes?
Yes, in short. So microbe is not a biological term in the sense that you can't say all these microbes are related. It's used to mean a free-living organism that you kind of need a microscope to see below the limit of the eye's resolution.
See, I'm told that the bacteria is bigger than a virus, and bacteria lives on living organisms, whereas the virus dies with the organism. Is that true?
Yes. So viruses, by definition, can only live inside a host or on a host. They can't free live. So if I have a tube of virus, it's not growing. It's only when it goes into a human or plant or whatever its host is that it can start to grow. And for that reason, people argue about whether a virus is truly alive or not, because it can't free live. There are some bacteria that can only live on a host as well, but broadly speaking, most bacteria live freely. And yes, broadly speaking, viruses are typically much smaller than bacteria, and bacteria are typically smaller than fungi, but there are some really wonderful exceptions. So there are these giant viruses, for example, that have been found in a cooling tower in France that are as big as some bacterial cells. There are some bacterial cells that are almost big enough to see with the naked eye, and there are some very, very tiny fungi. So yeah, it's not a hard and fast rule, but broadly speaking, that's the scaling.
So one of the problems that I've heard about dealing with microbes, especially in hospitals, is how do you clean a room? Because there's always one species of bacteria that's perfect for whatever your particular cleaning solution is. Is there ever a way that we're going to be able to finally clean a hospital room without setting fire to it?
Yes, I wouldn't recommend setting fire to your hospital rooms. It's a really good question, and you're absolutely right that the whole point about disinfection is you're trying to kill everything. But as we've just learned, some things are really quite hard to kill. So is there a way to completely sterilise a hospital room? Realistically, to utterly sterilise it completely is probably going to be quite challenging in a way that makes it still usable. I guess what you're worried about as a clinician is sterilising it from all the things that might do your patient harm. That's probably a bit easier. Most of the extreme organisms we've talked about are not pathogens, for example. Where it gets kind of sticky, actually, is in the diagnostic field, and you might be familiar with the fact that, so obviously now we do a lot of diagnostics using DNA, we sequence stuff, and you say, oh, look, this patient's got, X, Y, and Z. And one of the problems that has come to light in recent years is there are some organisms that are very good at persisting even in the factories which make those DNA kits. And so what you often find early on was a whole lot of patients with this weird bacterial species, I think it's Bradyrhizobium, that no one's ever seen in a patient, and we didn't understand that. And then we realised that that's because this bacteria is not in the patient at all, but it's living in the kit that you extract the DNA from. So there are problems like that you need to iron out, absolutely. But yeah, total sterilisation is probably a bit of a big ask, I would say. Sorry to disappoint.
Thank you. The slide that showed the E. coli dividing, there seemed to be one that was very long, not dividing. Why was that?
Oh, that's a very, very good spot. Okay, so yes, you're quite right. So when you have, that bacterium and many others grow by what's called polar division. So they elongate. It's quite clever. So they elongate, and then somehow they know where their middle is, and they put a new wall in, and then you have two cells, and you do it again and again. There are lots of mutations in which that process goes wrong. So you can have filamentous mutations where the bacteria grows, forgets to put the wall in, and grows again, and keeps going like that. And some of those processes, either by genetic mutation or just by random chance, do occur in a natural population. So when you see a natural population of bacteria, some of them are getting it wrong, basically. And actually, there's been a very interesting, slightly digressing, but a very interesting kind of series of work from people looking at mutants where they consistently get it wrong, and there's some lovely ones where, for example, they always go the wrong way, so they start to bend to the left, and they bend to the left, and they eventually go around in a circle, which is obviously not a very sensible way to evolve, but you can learn a lot about cell division in the process. So, I mean, without sequencing that very bacteria, I can't tell you, but my guess is that the one that grows that dividing has probably got an error in that cell wall machinery.
That might be helpful in curing that or eliminating that bacteria.
Absolutely, no, that's very astute. Yeah, so one of the ways that people look for antibiotics, for example, is to look for defects in growth. So a very easy screen is to look for bacteria that bulge out, and so instead of growing as nice rods, they bulge, which means their cell wall is not as intact. So a chemical that does that might be a useful antibiotic.
Now, on the slide that shows the bacteria in a rock, that bacteria must have survived extremes of temperature.
Yes, absolutely. So it's unclear from that particular sample whether it was deposited in the rock as it was forming, which would be massively, or whether there are kind of micro cracks that have allowed it to enter at a point, and then the rock has been pushed down through sedimentation and sealed afterwards. But notwithstanding that, there are certainly there are many species known, for example, from deep sea thermal vents where the water temperature is up at 200 degrees because it's under pressure, so it's not boiling, 200 degrees, and those bacteria are still fine. So there are certainly bacteria that can survive both very high temperatures and many, many that survive down into the minus 50, minus 60 degrees Celsius. It's quite remarkable.
Okay, one last question.
You talked about potential to learn, for example, from the bacteria or from the microbe that survives huge amounts of radiation for us. Do you have examples of have scientists already learned from other microbes that we use today?
That's a very good question. What have we learned practically from these? So in that specific example, Deinococcus, we have learned quite a lot from that bacteria about how a different way of repairing DNA. So the way it repairs its DNA, we now know quite well, and it's different to the way different bacteria do it. So it's able to repair what's called a double-strand break. So when your entire DNA is snapped, it somehow can figure out that those ends go back together and stick them, whereas other cells can only do that if only one strand breaks and you have the template. But perhaps the nicest example, and I haven't checked my facts, so I hope I'm correct, is actually from that rice blast fungus, where I'll show you the fungus attaches and then it pushes in. Now, if you think about drilling in, anyone who's done serious drilling, you've got to anchor yourself, right? Otherwise, all that happens is the drill goes up and down and you go up and down with it. You've got to attach yourself. So that fungus sticks onto the leaf surface. And I'm led to believe that a chemicals company back many years ago cleverly spotted the proteins that are used to stick it on and realized that these are serious glue and have taken many of the ideas from that to essentially generate really, really impressive kind of superglue materials. But I'm not sure, even if I knew, I'm not sure I should name the company. But there are certainly examples like that. And I guess that surface manipulation, lots of examples of people doing stuff like, learning about non-stick or shielding surfaces that resist UV by looking at these kind of organisms. So there's a lot of interesting learning you can do there. It's often the most unexpected areas, though, that yield those.
Thank you very much. Well, thank you very much, everyone. Thank you again, Professor May.
Thank you very much.
And please join us for Professor May's next lecture, How Microbes Manipulate Life, on the 22nd of March. Thank you.